Hello once again, AP Calculus AB students, Mr. Record here, and I'm wanting to talk to you a little bit about a special function, one of my favorite all-time functions. And if you're one of my students at Avon High School, you probably have in your notes for section 3.6 out of Larson's textbook, the very last part of that section deals with an activity where you'll analyze a certain function by the name of, and we'll type it in here to the tiNspire. For those of you that are tiNspire users, what I'm going to be doing here is defining the function f1 of x by using the control dock button. And then the function that appears on my students' worksheets is x squared plus a fraction, and that fraction ends up being having a numerator of the cube root of x minus 2 quantity squared, so basically x minus 2 to the 2/3 power, and the denominator there is 10. And when you hit enter and see the result done, that means that the calculator, or computer in this case, understands that that function is defined and all set to go. So what I'm going to do here, first of all, is I'm going to add another page, control dock, and I'm going to add a graphing page. And you'll notice that if we go up one level of our function, we'll notice f1 of x that we typed in, and all we have to do is hit enter for that thing to be recognized now by the computer. And you look at this and you think, hey, that's nothing really out of the ordinary. It looks somewhat like maybe a parabola. Well, I don't know about you all, but that comes as very unusual to me, because how could this function here that consists of this x squared term added to an x to the 2/3 power term produce something that looks like a parabola? Well, the fact of the matter is that this is anything but a parabola. And in order for us to really see what's going on, we're going to have to get a little bit more detail. We're going to have to zoom in a little bit here. And I'm hoping that perhaps if I gave you a moment to contemplate, for what value of x, for this particular function here, for what value of x does it seem like it would be pretty interesting to investigate a little bit? And hopefully you're all there thinking perhaps at x equal 2, given the nature of this here numerator. So what I'm going to do is go into my menu where I'm allowed to work with my window and zoom settings. I'm going to zoom box. I don't zoom box very often with my students, but I think that's an appropriate way to zoom in on this particular problem. And when you zoom box, you get to pick a corner. In my case, I'd like to do the upper left corner first, and then you'll drag from that location down to a lower right-hand corner, and you'll essentially make a box that would then become your entire screen. Now, I see a little bit something happening here when x is 2, which I have sort of the magnifying glass on top of. Seems like to be a little bit interesting characteristic of the graph. So I'm going to position this just above and to the left there, and I'll drag so that that value in question is somewhere in the middle. It doesn't have to be exactly in the middle of the box. But if I hit enter, I'll then notice that I've gained a great deal of detail into the graph, and I'm going to continue to do this upper left-hand corner. See, it looks right around in here. I got something interesting perhaps happening. Down to the lower right corner. Okay, and then we say, okay, where do we have the interesting characteristic of the graph now? I might lose it here, but I think it's right around up in here. So we'll go upper right-hand corner to lower left. And we think, the interesting characteristic, I think it might be covered up, so I'm going to hit escape just for the moment so I can drag this out of the way. I'm trying as best I can to keep this nice and centered, but I can see that we've got some strangeness happening right around that point here. So I'm going to have to go back in the menu, zoom window, zoom box, and we'll go above to the left and below to the right. And I think let's do that one more time. You know what? Let's go one additional time. There. I think that gives us a really, really sound piece of evidence that this particular graph is not that of a parabola. In fact, you guys would have all probably thought I was crazy if I told you initially that this graph had a relative maximum and a relative minimum other than the minimum that occurs down sort of at the vertex portion of that parabola-looking graph that we originally saw. And I can prove that to you very easily by going, hitting escape, getting out of zoom box mode, and going into menu and saying, oh, okay, well, let's analyze this graph. Let's analyze and see truly where is there a relative maximum. Well, if I start here from the left and I click and I move to the right, I sort of will be disappointed because it seems like every point that I get up to about here, the ordered pair 2, 4 is the maximum. Well, what would the minimum be then? Well, if we do the same thing, analyze graph for a minimum, I'll start left of where I know the minimum is going to be, and then boom, lo and behold, I get 2, 4 as well. Well, that can't be. You can't have a 0.24 be both the maximum and the minimum. Well, what we have to remember is that we've zoomed in so much that it's going to take quite a few decimal places to really distinguish these 2 points from one another. And on the tiNspire, one of the best ways to do that is to just hover over the, say in this case, the x value of the coordinate, and then I'm going to be hitting the plus button a couple of times, and I can get as much decimal accuracy as I want. And if I do the same thing, say for the y value, because again, I don't think that that's really going to be the case where they're both going to be 4, so I'll hit the plus button a couple of times to get some more accuracy. And if you think, well, could we do something similar with the minimum? Well, let's drag this very, very precise ordered pair for this maximum out of the way. And if I try to hover over the x value for the minimum and hit plus several times, I'm hitting it and hitting it and hitting it some more, I notice that nothing changes. Well, the reason is because that is the point 2, 4. When you don't get that sort of responsiveness from the tiNspire, adding more decimal places, then you can pretty much rest assured that you've got an accurate point. So interestingly enough, we have this maximum point, we have this minimum point. Now, if I were to return back to my calculator page, we could do some interesting things and verify this derivative is doing what it's supposed to be doing according to its sign. Probably the best way to take a derivative would be to go into the derivative menu, or the math template, I should say, to grab the derivative here. And then I can put with respect to x in the bottom, and then now just type in f1 of x, since I've already got the function entered above. And lo and behold, it'll produce a derivative. It will give us a little bit of a disclaimer down here about the domain that we don't need to worry ourselves with. And we could say to ourselves, well, we could test this particular derivative. We could take this derivative by going up and sort of highlighting it and hitting enter. It'll copy it and paste itself on the next entry line. And then I could evaluate this derivative such that, control equal with the vertical line, such that x is equal to, well, let's say I choose something that's going to be to the left of, well, to the left of what? Well, how about we pick something that's to the left of this very intense y value, 1.9999954. Notice there were 5 9s there. Well, I could choose to be somewhat conservative and pick 1.9. And I find that I have a positive answer. Well, if I do the same thing by cursoring up, copy and pasting by just hitting the enter button on your calculator, I will then be allowed to edit anything in this entry line. So how about I edit the value x equal, and this time I'll take it out to 6 places of 9, which you'll note is larger or to the right of the x value that we had as our x value of our actual maximum. So if this be the case, what kind of result should we anticipate for our evaluation? And the answer is a negative result. So you can see that we do change signs from our derivative of being positive to negative, and what better way to say that there is a candidate for a relative maximum in that location. We could also do the same kind of thing around the point where x is equal to 2. In fact, I've already got 1.9999999. We could then just edit this and go just to the right of 2, say 2.1, and we should anticipate a positive result to indicate that our derivative changed signs from a negative to a positive. Now, I didn't actually verify with this particular demonstration that we have critical numbers at this x value and this x value, but I think that sort of remains, or it's pretty obvious, I should say, that that's the case, because in order for these to be candidates for extrema, they must also be critical points first. But I thought that this is a very interesting function because, you know, you graph it initially and you can be quite fooled by the result. And I'm taking you back one more time to the original graph here. If I were to sketch this on a window size that's standard, we lose sight of the fact that, yes, indeed, we did have a couple of ordered pairs that played some very important roles, but they don't really look like they play very important roles on the normal, say, 7 by 10 window. Anyway, I hope you found this interesting, and I will see you next time.